Good afternoon. So let us continue the lesson. If you remember, I talked about R permutations last time, but we didn't solve any problems. Let me just refresh your memory about it, and then we can solve some examples. So I told you that, for example, assume that we have four distinct objects. Let me call them letters A, B, C, and D. And then for example, let me consider one more. If I ask you how many permutations are there, so the answer is very simple and straightforward, and that is 5 factorial. Because I have 5 distinct objects and I want to know how many ways that I can arrange them. But assume that I don't want to use all of the items. I want to have a sub-collection of the items and then I want to arrange them. Then of course I will have choices at 2 levels. One level is that which items I want to choose and then how I arrange them. Yeah, so I have two. So for example, assume that I want to write all 3 permutations. So this, in principle, what I calculated here is 5 permutations. But when I want to use all of them, I really don't need to emphasize, say, 5 permutations. I say how many permutations are there. But if I want to look at the permutations with less number of items in each, then I have to emphasize on this number. Okay? So for example, what do I mean by 1 3 permutation? Okay, so it means that I choose 3 of them, A, B, and C, for example. I can arrange them in this way. But even if I don't change A, B, and C, still I have different arrangements, yes? Yes, so these are all possible permutations if I choose these 3 items. I can choose A, B, and D, for example, and then I can arrange them again in how many ways? In 3 factorial ways. So I mean, each one of these things that you see is called a 3 permutation of these 5 objects. And if I ask you how many 3 permutations are there, it's a very easy task. You can actually solve it even just by the product rule. You would say that if I want to have a 3 permutation, it means that I have 3 distinct locations, and I want to fill each location with exactly one of these items. Then you would say that for the first location, I have 5 options available. For the second option, for the second position, I have only 4 options available because I have used one of them for the first position. And then I will have only 3 left for the third position. And according to the product rule, this becomes 5 times 4 times 3. So the answer is very simple. But I just want you to write this as factorials. So what you do, you write it 5 times 4 times 3, you multiply it by 2 and 1 yourself, but you are not allowed to change something, so you have to divide to compensate for that. And then if I ask you what can I write in the numerator, you can say that I can write 5 factorial, and 2 times 1 is 2 factorial. So of course the answer is so simple, but intentionally I wrote it in that way so that we can discover the general formula. By the way, we did the general formula. Do you remember? I told you that there are some notations to denote the number of 3 permutations. So assume that I have n objects, all distinct objects, and then R is a number between 1 and n, of course natural, and then I want to count the number of R permutations. So do you remember what was that? I told you that there is a symbol for that in the book, and mainly in many books they use it as P, I don't know, sometimes capital letter, sometimes little letter. So let me just write P and R. And some calculators write this on the bottom. And even in some books I have seen this symbol. So if someone asks you what is this, this is the number of R permutations if I have n distinct objects. And I don't know, do you remember what we got last time? We got that this becomes equal to n factorial divided by n minus r, whatever it is, factorial. Yes, so that is an important formula. It is also included in the formula sheet. But what is more important is to understand when to use it, yes? So for example, in this case, if I wanted to come up with this number, the answer is P. I have 5 objects here, and then I am interested in 3 permutations. So R is 3. So most of the time, if you write this, that's okay. But sometimes I ask you to calculate the number explicitly. Then it means that you put it into this formula. So n, here 5 is playing the role of n. So it goes to the numerator. And then r is playing, 3 is playing the role of this r. So this becomes n minus r. Whatever it is, factorial. But then the numerator becomes 5 factorial. 5 minus 3 is 2 factorial. And if you want to calculate it, it becomes 60. So it means that if I'm patient and I write all these permutations, each containing 3 items at a time, there are 60 items that you can see that I can write, yes? Okay, so that is the formula we want to solve some problems. You see that you really don't need to know the formula. Because even if you don't know the formula, you can use the product rule immediately to discover it yourself in the problem. But I really don't recommend you to do that. I want you to learn when to use this formula. So if I want to give you some rule of thumb, when this formula is relevant, when you have n objects, you see? So when you have n distinct objects, and then you have r distinct positions. Yes? Of course, what is r? R is at least 1, at most n. Yes? And of course, n should be natural. What you want to do, you want to distribute these objects into these positions. Of course, you cannot have enough space for n objects because n is greater than r. But then you choose r of them. Now r item is in your hand. Then you start arranging them in the boxes. Yes. The total number of ways that you can do this is called can be calculated using this. So something that I want you to know, it doesn't matter if I have, so let me write it with a different color. I can have distinct, I can have n distinct instead of objects, I can write positions, and then instead of positions, I can write objects. Let me make it better. And usually, I really want you to understand it in both cases. So it doesn't matter if the number of objects is larger than the number of positions, or the number of positions is larger than the number of objects. In any case, you can use this formula. Okay, but one of them is a little bit strange. Let me just tell you. For example, assume that I have 5 letters, and then I have only 3 boxes. So it means that I have to choose 3 of them and arrange them in these positions. The answer to this is 5, 3. But now consider I have only 3 letters, but I have 5. So let me number them. But I have 5 boxes. And of course, I want to start putting these into these boxes. In this case, some will be left empty. For example, one scenario is that I put A here, C here, B here. One scenario is that I put A here, C here, B here, and these are empty. Yes? So in this case, the number of locations is larger than the number of items. Here, the number of objects is larger than the number of locations. But in both cases, how many ways I can do it? Exactly this. Why is that? Because for mathematics, there is no difference between the set of boxes and the set of letters. If you don't like it, you can say that I want to assign a letter to, I want to assign a position to letter A. How many options are available? 5. I want to assign a position for B. How many is left for me? 4. I want to assign a position for C. How many is left for me is 3. So you see that I get the product 5, 4, 3. And if you do the same thing here you would say that I want to assign a letter to position 1. How many ways I can do it? 5, because I have 5 letters. Then 1 is used here. How many is left? 4. 2 of them are used. How many is left? So you see this number and that number are the same. So this is good to remember. If you have more objects, fewer positions, this is the formula. The other way around, the formula is exactly the same. Yes, so I want you to understand that. Any questions here? Okay, let me test your understanding. Before calculating, what do you expect the answer to this will be? I can use the formula to calculate it, but what is the answer to this? No?
It's not defined.
No, it is defined. No, forget about that. What is P and N? How many objects I have?
N.
No? So, yes?
N factorial.
N factorial. This definitely should be N factorial. I told you. P and R counts the number of R permutations if I have N objects. When I write Pn and N, it counts the number of N permutations of N objects. So what is that? N factorial. So the answer definitely is N factorial, but let us check. Instead of R, you put N. It becomes N minus N, which is 0. But 0 factorial, you remember by convention, and that is one reason why we have chosen that convention. 0 factorial is 1. And then the numerator becomes N factorial divided by 1, which is N factorial. So this is, I want you to understand, before calculating, and that is one main reason why mathematicians have chosen this convention for 0 factorial. Because if 0 factorial has been defined another number, then they have troubles, yes? Because this formula seems reasonable. That formula should also generate this one. This only happens if I choose 0 factorial to be 1. Yes? Okay, what do you guess about this one? Without calculation. You have N objects. No, be careful, yes. You have N factorial. Sorry, you have N objects. You choose one of them and arrange it. So in how many ways you can do that? N. Exactly, because you have N objects, you choose one of them. When you choose one of them, there is no point ordering them. You just take them and put them here. There is no ordering. So if you don't believe, we can calculate. This becomes N factorial, N minus 1 factorial. But N factorial can be written as N times N minus 1 factorial divided by N minus 1 factorial. And the answer becomes what? N. Yes? Okay. So now let us solve some problems here together. So,
Mike.
Yes?
A question.
Yeah.
If you show, so for the 3 permutation case that you wrote in the beginning. Does that account for all the different ones that you wrote below as well, or
Yes,
just the ones?
all of them. All of them. Because the only thing is that you choose and arrange. This formula takes care of both of them simultaneously. The number of choices that you have together with the number of arrangements for each choice. If you consider the whole package, this formula will give you the whole package. Yes, that's important to understand. But this is also important to understand. If the number of items and the number of locations are different, it doesn't matter which one is larger than the other one, the answer is the same. As long as actually the order matters. Yeah, here the order matters. So this is why I have all of them different. So let me now write a question here. So let us consider this word triangle. Yes. How many 5-letter words can be constructed using the letters in this word, 5-letter word? Okay. So that in each one of them, T and R are used. Yes? So the question is that I have this word triangle. How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8. My goal is to make 5-letter words. Yeah, let me solve it without constraint. Any constraint first. How many 5-letter words are there? In principle, you could solve this problem in the first session. But my goal is to repeat it and try to use these formulas as much as possible. But you don't need to be worried about using the formulas in the exam. In the exam, you can solve the problem in any way that you like to. But here, I want you to understand that we can use this formula. So what's the answer? So you know that when I want to construct a word, first of all, the order matters. Yes? Because if you rearrange the letters, probably you get a different word. So order matters, first of all. Secondly, I don't want to use all the letters because there are 8. I want to use only 5 of them. So it means that I have to choose 5 out of 8 and arrange them because the order is important. So because of that, the answer to this problem without any constraints is what? Just P 8, 5. That's it. If you write it, that's okay. But of course, if you want, we can practice a little bit in calculating the real numbers. So this becomes 8 factorial divided by the difference between them. No, n minus r. So it is 3 factorial. And then I have to write 8 times 7 times 6 times 5 times 4 times 3 factorial divided by 3 factorial if I really want to calculate. Then you have to spend time on multiplying this. That would be your number. Yes? But now, how many 5-letter words are there so that each word that I write uses T and R? How many of them, how many of these 5-letter words uses T and R? Yes?
P of 6 and 3.
So you say P of 6, 3. So is that right or not? Everyone else?
Yeah. Att T och R måste vara
Now, first of all, how many of you agree with this? Do you agree? Okay. can also open the chat window here if I can see. So what you are saying is that you want to use T and R. So it means that you take T and R away, if I understand your reasoning.
I disagree with myself.
Pardon?
I disagree with myself.
Yeah, I think you should disagree. Because the logic behind that is if I have a pre-assigned location for T and R, that is correct. But I haven't said where T and R are locating. I have just said that R and T exist there. Yes, so we don't know, are they starting with T, ending with R, where are these? What you have written is correct if I have already told you, for example, in how many of them start with a T and ends with an R, yes? In that case, this answer is correct. So, but now this answer is not correct. How can you correct your answer? So you have a 5-letter word, so it means that you have 5 distinct locations, of course. So location number 1, 2, 3, 4, 5. Why do I number them? Because order matters. I know that 2 of these locations should be occupied with T and R. And the rest should be occupied with the rest of the leftover letters. I will come back to you, Ruben, but let me repeat my advice again. If I ask you to write one of these words, do you really can do it or not? If you cannot do it, you are retarded, sorry. But if you can do it, it means that you should be able to count it. The reason that you don't do it because you don't try to find this, you don't take my advice seriously. Assume that I ask you to write a word like that. What do you really do? Just tell me. Okay, who is volunteer to say? Yes? Say one of these words that contains T and R. Just say it. Start with what? Any volunteer?
Triangle.
What?
Triangle.
So you say T, R, I, A, what? N. Is that what you mean?
Yeah.
So that's correct.
Try.
So this is when you can do it, in principle, above 90% you should be able to count it as well. So, but you need to look what your brain has done. Because you want to have T and R somewhere. So when you, I don't know, it might be because this task is so simple that you even care about what your brain does. But you really put T and R there somehow and then write the rest because you want to make sure that T and R is there. So this is a 2-stage task if you really care about what process is going on in your brain. Your brain decides 2 locations for T and R, and then the rest, you put the rest of the letters there, some of them there. So that is the way that you have to count. So this task can be considered as a 2-stage task. Yes? What is the first task? Can you just say it in English or whatever? What?
To position T and R somewhere.
Yeah. Positioning T and R somewhere. Just stop here. How many ways I can do that? So the problem hasn't started yet. So how many empty locations I have? How many empty locations I have? 5. How many objects I have?
7.
No.
8.
2.
I am considering only T and R now.
2.
I have 2 objects. The number of objects is 2. The number of locations is 5. And I told you that in this case, it doesn't matter if the number of objects is larger than the number of locations or the number of locations is larger than the number of objects. Yes? So the stage 1 is to assign 2 of these positions for T and R. In how many ways I can do that? No, forget about the numbers. Express it in P's.
P of 5 of 2.
P of 5 and 2. I have 5 distinct locations, but I have only 2 objects I want to arrange them. Yes? So this is the number of ways that I can put T and R here so that order matters. And now this is done. What do I mean by this is done? It means that, for example, I decide to put T here, I decided to put R here. Okay? And but is the task finished? No, because there are some leftovers. But T and R should be eliminated because I'm not allowed to repeat them. There are no repetition of T and R here. Now how many positions I have? I have 3 empty locations, but how many objects are left? 6. 1, 2, 3, 4, 5, 6. I have 6 objects, but this time I have only 3 locations. So it means that I have to make a choice and then arrange them here. In how many ways I can do that? In how many ways? No. So you are confused, I think. So how many objects you have? We have 6 objects, 3 locations. So the answer is P, yes, exactly. P, 6 and 3. Another thing that you have to be careful is the number that you write here, independent of how I located T and R here. It doesn't matter if I put T, R here, T there, or if I put R here, T there, this number doesn't change. So it means that by the product rule, the answer is actually this. Yes, is that understandable? So the one that you mentioned took care of the second stage, not the first stage. Yes, is that clear? So I mean that this is easier to look in this way. But of course, if you want the number, you have to calculate each one of them and then multiply. Okay, good. Let me ask you another question and wait for you a little bit, okay? Consider the word second. In how many ways we can arrange the letters in this word so that the vowels occupy the even positions? In how many ways I can arrange all the letters here in this word, but the constraint is that I want the vowels to be in even positions. So for example, one of the ones is the second itself. Because I have only 2 vowels, the position for E is the second one, which is even, and O is the 4th one, which is even. So that is acceptable. How many of these acceptable ones I have? Yes? Is the question clear first? Okay, just try to think it so that I can close the door.
Så det ska vara varje varannan. Mellan 2, 4 och 6. 6 är det 20 och det ska bli
Take my advice seriously. If you can write it, in principle you should be able to count it. I paused recording. Okay, do you have the answer? No? Yes, Ruben?
P of 6 and 2 times 4 factorial.
Thank you very much. Yes, that's correct. I don't know why it takes time for you to I told you everything what I told you. If you didn't understand, you have to ask me. Because I told you that. If I ask you to write a word so that E and O occupy even positions. So how many positions do I need? 1, 2, 3, 4, 5, 6. So I have 6 locations.
Yeah.
What I'm supposed to do, but I have only 2 vowels, and I want to make sure that the vowels are occupying actually even locations. How many even locations you see? 3. But how many objects I have?
2.
Okay, I want, and order matters. So then what's the answer? To put E and O, the answer would be I have 3 locations, the larger value, and then I have 2. So that is the total number of ways that I can arrange E and O in 2, 4, or 6. Of course, one of them will not be occupied at the end. Only 2 of them will be occupied. Yes? Because I have only 2 vowels, but I have 3 locations. This is a stage 1. By this stage, it means that I was making clear about what is happening for E and O. For example, I decided to give this location to E, and I decided to give this location to O. This is one possibility. Now, what is left? 4 locations are left. This thing. How many objects are left? 4. 4 objects, 4 locations. Order matters. So it becomes 4 factorial.
Order of matter. Matters. Of the concept.
And then you multiply that.
Permutations.
Thank you. Is that understandable or not? This is my advice. In combinatorics, try to be very simple. Don't make things so complicated. Because the problem is not complicated. When I ask you to write a word like that, every one of you can. But when it comes to counting, you start complicating the problem. Exactly do that. If I really want to do this, E and O is more important than the others because I have a constraint on them. So my brain makes it clear where I put them to relax and then occupy the rest. That's the way that my brain works, and every one of you works in this way, even if you don't think about it, but you really think about it for a very small fraction of a second. Anyway, is that understandable? That is the answer to this problem. Yes? So these 2 problems I consider standard problems because I am just taking care of these 2 options. Yes? Yes. Now let us make the problem more interesting. Okay, so before making it more interesting, let me ask you something. So I give you let me work with numbers. 1, 2, 3, 4, 5, 6, and 7. Let us do some recap. In how many ways I can use all of them and write a 7-digit number? Only using these so it's not a good way because you might say that, okay, I can repeat 1. Now let me how should I express it? I don't want you to repeat the digits. So that's not a good. So let me write it like this: A, B, C, E, F, and G. Okay. Assume that these are people. I am naming them. Person number 1, person number 2, person number 3, etc., etc., etc. In how many ways I can put them in a queue line? 1, 2, 3, 4, 5, 6, 7 in a queue line. So 7 factorial. Now my question is that if these 2 people hating each other, in how many ways I can put them in a queue so that they are not immediately next to each other? At least there is a barrier between them. Yes? In how many ways I can do that? So they are not, so these 2 people have problems? in how many ways I can arrange them in a queue line, so the order matters. I want to use all of them, but I want to make sure that they are not immediately next to each other. At least, I'm saying at least there is 1% in between. I am intentionally making the problem a little bit harder by saying at least or whatever, but you need to be smart enough to understand how you should do the problem. So the people at home, because I want to give time, this problem is clear, yes? Let us see if you have any ideas.
Baba,
Yes?
is it only between A and B?
Yes.
Yes.
Okay.
So these two people are not getting along.
Two faces. Yeah, place A och sen place B.
Okay, so if you don't mind, let me pause the video recording. You can think.
Jag tänker att det här är ju...
Okay, any ideas?
Och sen så gör du samma sak för D-paret.
Yes, Ruben?
7 factorial minus 12.
Minus 12.
Yeah.
Your idea might be right, but I don't know why 12.
Well, I thought 7 factorial is the total number of ways, yeah. And then minus the times where A and B are close to each other, which I thought was...
Your strategy is completely right, but that minus 12 is strange. So the idea is completely right. In this problem, it is very nice to use the complement rule. So you were trying to use P rule somehow in your brain, but this P rule will come later. I started with a simple problem now. Yes? You want to have A and B close together, yes?
12 should be correct. Because there are 7 positions and they have to be next to each other. So you place them next to each other, you can fit that 6 times. And then you can switch places.
No, you can also switch a lot of people around that.
But you should multiply 12 by...
No.
Yeah, okay.
No, put these people, for the time being they hate each other, but put them momentarily in the same box. They kill each other in that time, but in that time, so that, do you remember the books? I was talking this problem of the books, math books next to each other. So that's exactly the same thing. So your strategy was completely right. That was a little bit of misunderstanding. That's completely right. So you calculate the total number of ways that they can stand in a queue without any constraints. This is simple. 7 factorial.
Yes.
In some of them, A and B are next to each other. In some of them, A and B are away from each other. But now I want to ask myself, in how many of them A and B are next to each other, immediately next to each other? How can I count? This is a standard in combinatorics. This means that momentarily I put them in a box, and then how many objects I have? I have 1, 2, 3, 4, 5 objects and a box. I start moving them around. In how many ways I can do that? 6 factorial. But these people inside the box can also change, so I multiply it by 2 factorial and then subtract. That's the answer. Might be 6 times 2, you wrote that 12, yes? But this is not, this is the case. Understandable or not? Yes? Dennis, you are not happy? No, this is my advice. In combinatorics, the examples that I solve here are standard examples. You have to use them as anchors, so that when you come to another problem, try to fit your problem with those standard problems. Otherwise, it becomes extremely hard. So one of the examples you need to have in mind as a prototype example is that I want to arrange items next to each other, and I want to have some of them immediately next to each other. Topics, people like each other, whatever. Yes? So, let me ask you one question. Forget about this minus sign. I am asking you, assume that these 2 books are physics books, distinct physics books, and they are different topics. I want to arrange them in a shelf so that the physics books be exactly next to each other. That's the same problem, yes? So I put those physics books in a box because I had this standard problem. Of course, if you use your memory somehow. Then this becomes one object, 2, 3, 4, 5, 6 objects. One of them is a package, and then I have 5 more books. In total, I have 6 objects. I start arranging them, but in 6 factorial ways. Whatever I do, this box moves around, and it carries both A and B. So in all of them, A and B are next to each other. But I have an option of 2, because A can be here. It can start with the A, it can start with the B. So that's a 2 factorial. So this number that you see is the total arrangements so that A and B are immediately next to each other. On the other hand, 7 factorial is the total number. If I subtract them, it means what is left are the ones that A and B are not immediately next to each other. And that was my goal. Is that understandable? But now, the interesting problem starts here. Okay? Instead of 2, 3 people start fighting. Yes? And then they mutually fight. It means that A hates B, B hates A hates C, C hates A, B hates C, C hates B. Yes? Now, now what will happen if I want to keep peace? Yes? A, B, C, D, E, F, G. Is the question clear? I want to arrange them in a way that at least one person is between A and B, one person is between B and C, at least one person is between A and C. Now this is more interesting question. Now let us first ask, is the question clear? So in the arrangement that you show, for example, is it acceptable or not?
De måste vara varandra. Det finns ingen annan val.
Det här får aldrig
Det är det jag tycker är sjukt.
oavsett vilka platser.
Is it an acceptable arrangement of these people? A, B, C, D, E, F, G. I don't have this. Is it acceptable or not? Yes, because you see this is an arrangement of these. Between A and C, I have some people. Between A and B, of course, I have a lot of people. And between C and B, I also have some people left. That is one acceptable arrangement. Yes? But if this one, A, and then I have C here, D here, E here, G here, F here, B here, this is not acceptable because even though between A and B, C and D, we have quite distance, but there is no distance between A and C. This is not acceptable, this is acceptable. I want to count all acceptable ones.
När alla de är med varandra, då har du en 5 faktorer gånger. Alla de här är samma. Alla de här kommer ha det här svaret.
Okay, if the question for the people that don't clear, I will pause recording. Okay? Okay, let me write something here. How many of you thinking about this number?
Och då är ju det här motsvarande det här.
How many of you are thinking about this number? No. So, but I just want to tell you, if you're thinking about this number, that number is wrong. Yeah, so it's good. So if you know that this is wrong, that is actually very good.
But the other part,
Yes, someone?
Is it 7 factorial minus 6 factorial times 6?
No, I don't know. The number that I have in my mind is different. Might be you have a different strategy in counting. But you need to tell me what is your strategy.
So I thought I did the same thing, the complement rule. So I calculated each time A was with B, and A was with C, and B was with C.
Yes?
Then I subtracted from the
But that is not exactly what I want. What is left is not exactly. Do you agree with me? So what Amanda is saying, at least let me tell you why might be people thinking in that way. They say that, okay, we want this. What is this counting? This is counting the total number minus all of them to be next to each other. But that is not exactly what is left is not exactly what we want. Yes, because in this item we have this acceptable.
Yes.
A B C A B D C E F G. This is being counted here. Yes, because this tells you that I am subtracting the items in which A, B, and C are simultaneously close together. And this is now A, B, C are not simultaneously close together. They are not immediately next to each other. So this is not subtracted. This is left over. But this is not acceptable because now A and B are next to each other. So this way of counting is not right. Now Amanda said something else. So you said that I calculate what? The number of ways that you calculate, you put A and B next to each other. So if I put A and B next to each other, how many ways I can do that? 6 factorial, 2 factorial.
Yes.
This is the total. And then you said, once more, I put A and C next to each other. Yes? So that would be the same number. And then once I put B and C next to each other, that would be the same number. So I will subtract this minus 3 times that. Yes? Which becomes, as you said, 7 factorial minus what? 6 factorial times 6. So, and this number, if this is going to be right, this is 7 times 6 factorial minus 6 times 6 factorial. So your answer is actually very simple. And the answer is 6 factorial. Okay? Okay, I'm not saying that this might be wrong because this turns out to be 6 factorial. But let us see what is the flaw in this calculation.
It doesn't account for one case, and that's when all 3 of them are next to each other. You need to subtract that case too.
No, it actually, I think...
because I have that answer and then I subtract another case when all of them are next to each other.
But,
It's A,
No,
C,
so-
and B and C can never be.
no, you see, in this case, you are considering A and B next to each other and then you are subtracting it. A, B. Okay, so let me write A, B, and C, D, E, F, G, H. So, sorry. You are counting this at least 3 times. No, 2 times. Yes? This item is not acceptable, I agree. But you count this item once A and B are next to each other. You are subtracting it. Once you count the same item when B and C are next to each other. But you are subtracting it once more. Do you understand what I mean? Because when you put A and B next to each other and subtract, you already subtracted this item. But then, when you are putting B and C next to each other, you are subtracting the same item once more. So it means that you are actually removing a lot of items more than once. Is that understandable? Is that clear or not? Okay, so this is not the correct number. And it turns out to be a very hard problem. It's not a simple problem. It needs a complementary rule that you haven't studied, and you will study probably in university. That is called exclusion and inclusion principle. If you want to solve it using complement rule, if you insist to do that, yes, it is possible, but it is not a simple version of the complement rule. So that is called inclusion-exclusion principle. As actually Amanda did, more or less the idea was right, but you are subtracting items more than once. You have to add them again and subtract them again. So that is inclusion-exclusion principle. Yes? So my advice is that find another strategy. Either you really need to understand what is going on, because this is a very good example I want to mention. So you see, once you subtract it from here, so that's exactly, by the way, that is exactly like the set. Yes? So if I consider what Amanda is saying is that A and B are next to each other, here A and C are next to each other, here let us consider B and C next to each other. But there are some overlaps between these sets. Yes? And then what you are going to count is outside this. And that is inclusion-exclusion principle. And actually you can do it by the set theory if you want to. So you want to calculate how many items are outside. So then this means that you need to count, if this is the set A, this is the set B, this is the set C, you are interested in the cardinality of this minus the cardinality of the universal set. And if you remember in set theory, we had a formula for that. So that is a very long formula. That works, that is correct. But my strategy will be very simple. I want you to understand that strategy. Can you find another way? At least this is very good because you understand. By the way, if you are really patient and interested in combinatorics, I really recommend you follow what Amanda said, but try to correct it using the right version. In principle, you will get the same answer that we will show you here. Now let us try to think a completely different way. Can you think a completely different way? Let us go back to the two-person case. And I want you to think again, my recommendation, you really want to do the same thing. You know who are not going along together, you want to put someone there. So what is one strategy to do?
To divide it into two tasks, two stages.
No, assume that you really have people. Imagine that your friends are here. There are 7 of them, and you know that 2 of them are not going along with each other. So what you want to do, you can... one way to look at the problem, I don't want to spoil the problem. Do you have any other strategy? Consider only this case. This was completely right, but let us look at the problem in a completely different way. Okay, so my strategy for this problem that can be extended to all cases is this. This is not my strategy, but I learned this strategy, by the way. When I say it's my strategy, it's not I invented that. Okay, but this one, I would say that forget about these 2 people. They are making headache for us. Let us arrange these people. They don't have any problems, yes? So in how many ways I can arrange them? Forget about these people. Throw them away. So 5. So it is 5 factorial.
Okay, so
and then I start arranging them. For example, C, D, G, F, E. This is one arrangement. Yes? And then I realize that 2 people are there. What can I do now?
You can place them.
I can split them a little bit around. Okay, I decide to put them here. So I put one of them here and one of them there, for example.
Yeah.
Or I can choose to put one of them here, one of them there.
Yeah.
Or I can choose to put one of them here, one of them there. Is that clear?
Yes.
Okay, in how many ways I can now arrange these 2 people?
6.
No, be careful.
6
Oh, no.
factorial divided by...
No,
Nah.
2 people are different. They
Ah,
are not
then-
the same objects. Yes? So you see, 5 factorial, I arrange these people in 5 factorial way. How many empty locations I get? 6 empty locations.
but times 2.
P62.
P62.
Yes.
Is that understandable?
Yes.
Yes.
So another way to solve the problem is to multiply it by P62. If you don't believe, let us calculate the numbers. So this is 5 factorial. Yes? P62, what is the answer? 6 factorial divided by 4 factorial. Yes or no? But 5 factorial can be written as 5 times 4 factorial. This one and that one are gone. So the answer that is 5 times 6 factorial. Yes? Let us calculate this one now. 7 factorial can be written as 7 times 6 factorial. And then I have minus 2 factorial is nothing except 2, and then 6 factorial. I have 7 6 factorials, 2 of them are gone. What is left? 5 is left. So this answer and that answer are exactly the same, but totally different strategies. This is using complement way of thinking, but this is just the product rule. Is that understandable? You're not happy, are you?
I had a different strategy for the first.
No, you can. I can hear that, but let us say, do you understand this strategy at least? It's a very nice one because it doesn't use the complement rule at all. The way that I am thinking is not the complement way of thinking. I'm just using the product rule. Now let me hear your strategy.
I split it up into 2 stages.
Yes?
And the first stage consisted of placing the people that hate each other.
Okay.
Uh,
Where?
In 2 different ways. So I
No,
split-
where? Do you have already your locations? So do you have
No, they
seats?
have, 7 empty positions.
Ah, okay. So you have 7 empty positions. 1, 2, 3, 4, 5, 6, 7. Yes. You have 7 empty positions, and then
And then if you place, the first step is then split up into two ways of doing it.
yes.
Either you place a person that's hated on the first or last.
Okay, but that becomes a lot of cases.
It only becomes 2 cases.
I don't. Okay, I want to hear from you. Okay, so tell me what to do.
Either you place, let's say A in the first or last position,
Okay.
and then you get, there's 2 available positions for that one, and that leaves 5 for the other person. I can show you afterwards.
Yeah, no, but because I want to. It is not that easy. Probably you are. So let make it very clear. So you have the first person A, and the second person B. Okay, tell me what to do with these people.
The first case is A is placed first or last in position 1 or 7.
Okay, so it means that you, in 2 different ways, you can put first A either here or there.
Which leaves 5.
So it means that now this is done. It is done. It means that, for example, you put A here. Okay.
That leaves 5 positions for the other person.
No, but still this is not occupied.
No, I mean, yeah.
Exactly.
B can be
So,
placed
1 to 5.
In every position except for 6.
Ah, okay. So what is your okay? So you mean that I take this person and assign it either to number 1 or 7. I can do it in 2 different ways. This 2 is because of that. Now either 1 or 7 is occupied by A. So okay. So this is gone now in my head. I will have this one. But you say that, are you talking about B now? In B, am I allowed to put it here or not? Yes, here. So 1, 2, 3, 4, 5, 6, except that one. Yes? So this means that 5. Now B is somewhere. For example, let us, for the time being, put B here.
Yeah, and then the other case is that you put A in a position not on the ends.
Okay, but what about the rest? You want to take care of the rest at the end?
We're still on stage 1, trying to figure out where you can place A and B.
Okay, okay. Or
You place A in a position in the middle, so 2, 3, 4, 5, or 6, which means 5 positions.
3, 4,
2,
5.
2, 3, 4, 5, 6.
Here?
Yeah.
I put A here somewhere.
Yes.
Okay, 1, 2, 3, 4, 5. So I choose, for example, to put A here.
And that leaves 4 possible positions for B.
Okay, except these 2, yes?
Yeah.
Yes?
So those are all the ways you can place A and B in the 7 empty seats without them being next to each other. And
So the answer becomes now, yes. So it becomes 6 times 5. Okay. And then
this stage 2 is placing all the other people.
so which is 5 factorial, because 2 of them now are occupied, and then 5 empty places are left. Yes?
Yeah.
Okay. But let me first, to cheat a little bit, is the answer that answer? I think it is.
The answer is 3,600.
Yeah, that's correct. Well, I mean that I should be able to find this one like that. 6 times 5 times 5. And then this one times that one is 6 factorial, and then I have a 5. That's correct. Yeah, that's good. That's a very good strategy. Yeah, that is working. Yes? But still I believe the other one was simpler.
Yeah.
Yes? Is that clear? Now, the reason that this is simpler, because my method can immediately be extended to that case that 3 persons hates each other. Your method will also work, but it will be very complicated. Yes? Yes, but that's very good that you have this. Very, very nice. Thank you. Okay, now let us solve that problem for the case that 3 people, they don't want to be next to each other. Yes? If you learn this strategy, it is very simple now. Okay, should I clean this now? No, we can keep it. I can clean this. Okay, I pause recording because now the answer to that problem becomes very simple. I want to hear it from you. The same problem. A, B, C, none of them be adjacent. Okay, what's the answer? Yes, Ruben?
4 factorial times P5, 3.
Yes. Yes, thank you. Why is that? So now the strategy becomes clear. So you have this, if you are interested in combinatorics, you need to know, send it to your memory. This is standard problems. So here we have A, B, C, D, E, F, G. I have problems with these 3 people, so I ignore them for the time being and arrange these people. How many ways I can arrange these people in a row? 4 factorial. Yes? So assume that I did the first stage, meaning that I arranged them in some way. Then I get one location here, another location, another location, another location. I am putting circles for all of them, but I hope that you agree these locations are distinct. Why? Because I can address it. I can say this location is left to E. I can say this location is between E and F. So this location and this location are different because I can address them. Yes? So these are distinct locations. How many of them are there? 1, 2, 3, 4, 5. Then it is clear that I have to put these people in these three of them. I need to choose 3 of them and put these people there. So in how many ways I can do that? P, 5 positions, 3 distinct objects. The product is your answer. Yes? So you see that this is a good method because it is very easy to extend it for higher numbers. Yes? Let me test your understanding what you remember from the previous sessions by giving you this example. Any questions here? Understandable? Okay, this word, Masasago, it's something like that. What is this? So let me see. M-A-S-S-A-S-A-U-G-A. Yes. Consider this word. Masasaga. Yes, something like this. Okay, my question for you is this. In how many permutations of the letters of this word, none of the letters M, U, and G are adjacent? So let me just repeat. I don't write it because we want to finalize this problem as well. So consider this word. In how many arrangements of the letters of this word, no pair of these three letters are adjacent? So it means that M and U are not adjacent, M and G are not adjacent, U and G are not adjacent. So in how many permutations I have this condition? So if you want, I can arrange it a little bit better for you. So M, A, S, S, A, S, A, U, G, A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that is your word.
Min kombination av en av de förra problemen och det här nya. Du kan inte ha nej, det slutar räkna med caset som just så då säger du att du räknar A som en individuell bokstav, men det finns 4 A. Så du räknar samma case 4 gånger. Så du måste dela 7 faktorial dela och 4 faktorial gånger 3 faktorial. Det är din första.
Any answers? Or any strategy? Yes?
Wait a second.
You don't need to give me the answer, you just tell me what to do. So, the lesson that you realize here, the way that you don't want to put things next to each other has a very nice strategy.
Positioner. Du kan placera de här 3 innan det första A. 1 och sen mellan 2, 3, 4.
I don't understand, why don't you answer?
But we have an answer.
Okay, just tell it to me.
Do you
I
want
don't know, because if you give me the numbers, I cannot realize. What is your
I
strategy?
can give you the strategy.
Yes.
So you you assign all the other letters,
Exactly.
and then but you this time, because there's multiple of the same letter, you need to divide
Exactly.
to exclude
So
those cases
exactly
as well.
again. So for the time being, throw these guys away and just concentrate on these people. Yes? How many ways I can arrange 4 letters of A and 3 letters of S? This is a standard problem. If you want to solve everything from scratch, this becomes extremely hard. So this means that based on what I learned here, for the moment, I don't care about the people who are not getting along with each other. I just throw them away and then try to arrange these numbers, these people. So this becomes 1, 2, 3, 4, 5, 6, 7 factorial. But 4 of them are of the same type, so I have to divide by 1 4 factorial. And 3 of them are of the same type, so 3 factorial. If you ask me what this number is, I would say that this is the total number of arrangements that I can make with 4 A's and 3 S's. Yes? But if I have 4 A's and 3 S's, for example, A, S, S, A, S, A, 1, 2, 3, 4 trees. That's it. Then, how many locations I have to put them in? How many opportunities I have for these people? Either here, here, and 8. There are 8 open locations that all of them are suitable for these people. Okay? 8 locations, distinct. These 3 letters are also distinct. So it means that in how many ways I can arrange 3 distinct letters in 8 distinct positions? The answer is P, the larger number 8, the smaller number 3. And then I have to, what should I do between these two?
Multiply.
Multiply. So the answer to this question is 7 factorial, 4 factorial, 3 factorial. And if you want, you can open this up. It becomes, I don't think it becomes simple. 8 factorial, the difference between these two, 5 factorial. So the answer seems a little bit strange, but this is what it is. 3 factorial, 4 factorial, 5 factorial. That is the answer. Yes? So remember, I don't know, so if you don't remember these standard problems, then it is hard. Because every time you have to start from scratch to solve the problem. Is that clear? I still recommend you to solve this problem for 3Ks using this set theory idea. But that's also very nice if you can solve it. And we already have the answer, yes? The answer, you can simplify this answer to see what it is, and this you can calculate to see if you get that. This will teach you a lot of things. Any questions? Thank you very much.